Good evening to everybody. Thank you for the invite this beautiful session. Thank you to all of you that are attending, and special thanks to some friends and colleagues that they are currently in Mexico and Costa Rica. They decide not to go to the beach and listening my talk. Today my talk is going to be quite general. I'm not going to talk about something in specific because I thought that the audience is a quite broad audience and I don't want to talk about some specific project I'm working on in finance. I thought instead it would be nice to have a generic topic like Bayesian modeling that can be interesting to everybody, and I hope you, after this talk, the one that didn't use, you're going to use Bayesian statistics. The aim of this talk is to just send a message that Bayesian inference and Bayesian statistics is quite simple theory and very powerful and elegant at the same time. So I'm gonna set the why do we need Bayesian inference as a beginning. Then I'm gonna show you like a very simple example how you can use it in practice. And after this, I'm gonna talk about some more complex problem that you can solve in real life. And I hope that the message is transmitted. So why do we need Bayesian statistics? Let's start with a little example that is I was facing when I was 18. So when I was 18, I got the second-hand 500, which was not the oldest one, not even the new one, but the one in the middle, right? So just to let for the Italian audience, let's say. And basically, when I had this car, I was 18, and I had some kind of random income. And I was afraid like to put more than €5 as a gasoline. After a bit, I realized that actually all my friends, they were doing the same. So every time I was getting into the car of my friends, I was seeing exactly what I was seeing in my car. So these orange light flashing at your eyes. Now, clearly, as you can see, if your friend is come to pick you up to go somewhere, you know that you're taking a risk, right? So the risk not to arrive at destination. Now, the problem is that if your friend is coming to pick you up at Lambrate to go in Navigli for an aperitivo, so you're gonna take the risk, right? Because your uncertainty is not that big. I mean, at worst, you take a taxi to go home. Instead, if your friend is going to pick you up in Lambrate to go to Pavia, I mean, now the uncertainty is a bit higher, even if you trust your friend, or most of the time in these cases, he says, don't worry, I know my car, we will make it, right? So anyway, the uncertainty is becoming a bit like higher. And the worst will be if you need to cross the desert between two cities. I mean, you will never get into the car, right? So basically, we have two different concepts, the concept of risk and the concept of uncertainty. I like to highlight these two concepts because when I start working in finance and I was presenting Bayesian statistics to some investors, some of them, they were saying, what, risk and uncertainty? But this is the same, no? Actually, this is not the same, and you will see why it's not the same, but somehow they are connected, right? Because the higher the probability, the more is like, the higher is the risk. So the more uncertainty there is in determining the risk. Another little example with this beautiful painting by a Dutch painter. So this painting is, the title is The Conjurer. I would like to call the guy in red to the right like the magician. So basically this is the game of the 3 cups and 1 pea, right? So basically you have the magician who is putting the pea below one of the cup, and then just with some trick moving the cups, you have to guess where the pea is, right? Now imagine that you are an investor and you see
I'm sorry, excuse me, we can't see the presentation, I think.
You cannot see it?
Yes.
It's blocked to the first page.
Okay. Now you see my screen?
No, maybe you have 2 screens, no?
Yeah, you are using the wrong one, probably.
Okay, maybe.
I think, Giacomo, you should directly go into the presentation mode.
From where? From
on the top right, you can see that present.
okay. Actually, I think. Okay. Stop. Can you see something now?
Yes, we can see the screen now.
Okay.
Try to change the page. Perfect.
Can you see it?
Yeah.
Yes.
It works.
Okay, this you already saw, right? So I don't need to come back to this. Okay. Yeah. So basically you have the 3 cups, right? And you have 1 pi below one of the cup, and you need to guess. Now imagine you are an investor and you found a very good opportunity to invest and you decide to participate. Now your risk is 1/3, right? Because the probability to find the P in one of the 3 cup is 1/3. Now, if we measure in the risk of losing as the probability of losing, so the probability to lose is 2/3. Now, since you don't want, if you are very careful and you do your due diligence very correctly, before starting playing, you observe the game. And actually you realize that the magician is very good in moving the hands and doing some trick. So basically the risk is not anymore 2/3. I mean, the probability to win is not 1/3, but you kind of have some uncertainty. At the same time, if you look at the left, there is a pickpocket, right? So then basically what happened, the wallet picker is stealing your money. So the uncertainty to win is bigger. Now, that's why I was saying the uncertainty is very important, because now the probability to win is not anymore 1/3, but now we have also uncertainty. Okay, this is the width of the curve that I draw here is the uncertainty, right? And the risk now is not anymore like before 2/3. It can be higher. Actually, the probability to win, it's pretty much 0. So now that basically I settle the motivation of why we need Bayesian statistics, because Bayesian statistics, as you will see, is introducing the risk and uncertainty. So basically we can measure the two. So basically we can measure the strength of our beliefs. So now, not to scare you, it's just very simple mathematics, and I just put it because it's very simple and elegant. So how do we put this in mathematics? This is exactly how our brain is working. When we see a new phenomena and we have to take decision, we make first an hypothesis. Once we have an hypothesis, we create prior beliefs. So for instance, in the case of the game of the 3 cups and the beans, we make an hypothesis that the game is fair. Then we have a prior belief. Our prior belief is like we have 3 cups, 1 pie, probability to win 1/3. And then we start to observe the data. But while we are observing, our belief is updated, right? So then we create slowly a posterior belief. This is exactly, I mean, these are the keywords of Bayesian statistics. How do we derive Bayesian statistics? Very easily. These come from the basic rules of probability, right? So imagine you want to calculate the probability of the ensemble A and B. So this is equal to the probability of A plus the probability of B minus the probability of the interception. Why? Because we are calculating twice the interception area, right? Now, since we have a symmetry of intersection, so we can write the intersection like the conditional probability A given B by the probability of B. But this can be written also, since it's symmetric, right? The probability of B given A by the probability of A. Now, if we divide the second two part of the equation by PDB. So as you can see below, we get the Bayesian rule. This sometimes is called like Bayes theorem, but actually it's not a theorem, it's just a constant. So you just start from the basic of probability theory and just you rewrite the position of the members in the equation, right? That's why it's sometimes called Bayesian rule. Now, as you can see here, these are numbers, right? There is a theorem that can be extended into probability density. I put it here very big because this is the final result. With this, you can do many things, as you will see very soon. And this is very beautiful, right? So in the green, you have what is called the posterior probability, given hypothesis. Here I called M as a model, given your data. And basically, you do prediction on the parameters data. With this probability, the posterior one, we can make prediction, as you will see. Instead, the red term, which is sometimes very complicated to calculate, that's why we need numerical Monte Carlo or variational, Bayesian statistic, whatever. But with this, we can do model comparison. So basically, you can decide to describe your data with one model or another model, and then you can check. You can do the comparison thanks to this red term. In the numerator, instead, the first term is called likelihood. And this is the probability that your data are well described given the model and the parameter data. And the other term is the prior knowledge. For this moment, in the next two slides, I will talk about the likelihood only, okay? So imagine you are a data scientist and you are hired by Poste Italiane, right? So Poste Italiane decide to open a new office in Milan, and they call you because they need to understand, so they need to calculate the average time spent by the client at the curtain, right? So basically, this is the typical problem. So you have a lot of customers, which are like represented here by little dots, and they spend time at the counter with the operator. So, and this is the X time, is the time spent at the counter. So in this case, I choose like a time frame between 0 and 35 minutes, right? So as you can see, many of them, they spend like around 4 minutes at the counter. So the hypothesis that you take most of the time is that the time is distributed like exponential, right? Now, this is a typical problem that you solve at high school or maybe at the first year in physics. For those of you who studied physics, this is the same problem if you have like a source of nuclear particles that they decay, and the x-axis you have the length of decay, right? So to calculate the length, the path performed by each particles, and to calculate the decay, you basically do it with an exponential distribution. It's exactly the same. Now, if I ask you, imagine you have no knowledge about Bayesian statistics and whatever, how do you calculate the average time spent at the curtain by the customers? The first thing you do is like, well, I divide the x-axis by bins. I count the number of participants or clients in each bins, and then basically you fit with exponential, right? So you decide to optimize using gradient descent, whatever. So basically you do this. But now my question is, how big is your bin, right? Is this one, or is this one? So the data, they didn't change. I just changed the width of the bin. This is a problem, right? But you have also another problem. The other problem is that you need to fit your data with a theoretical curve. Here is the red line. How do you measure the discrepancies between your theory and your data? So you have to decide also the distance, the measure of the distance between the experimental data and your theory curve, right? So you can choose the last square, the least square, you can choose the absolute value. There are many opportunities. I'm just saying very few examples, but you can choose many different ways of solving this problem. The problem of a classical approach is that you always need to define some parameters in advance to do the inference, right? But again, we know Bayesian statistics very easily. Again, here, just to remind again, the Bayesian rule with the green and red element in the equation. So what we need to do is just writing the likelihood, right? So our hypothesis or our model, because here I called M, is that our data will be described by an exponential distribution, decay, right? This is the hypothesis. So basically we need to define here I called lambda, right, which is the typical decay time for the exponential distribution. In the equation above is theta, just to indicate that the parameters can be many. In this case, we have only one parameter. So the likelihood is very easy, right? So you write the product of all the function calculated at the point, right? Here I call just xn. So in this picture is the solution, right? The more data you put in your equation, the better is the solution. The more the curve is shrinking, so which means the uncertainty is becoming smaller and smaller because you are more certain about your distribution, and you get the final result given the data D, the data set, which is the black line, right? Now you can say to your manager, the time spent at the counter by the client is around 5 minutes, but you don't have only one number. You don't give a parameter, you give the full distribution, and you say also, this is between 4 and 6, right? So you have an interval. In the Bayesian statistics, this is called credible interval, right? However, some of you, who is also very smart data scientist, says, hey, but I know that the new office is open in an area where there are a lot of students and a lot of retired people. So now basically what you can imagine is that old people, they spend more time at the post office with respect to the young people, right? So basically you want to modify your model and you say, well, at this point, I want to modify my model, and I take into account that some of them, they're young, some of them, they're old. This way, I will have two different specific decay time, right? So you have what is called like multimodal distribution. But your manager is not telling you who is old and who is young. He's not giving you this categorical variable for describing your client. So you have to make assumption. Actually, you can take this distribution, just by changing the colors. Basically, you have to rewrite your likelihood. Or here I use the little trick used in probability theory, which is the chain rule, right? So if in this case, we have lambda 1, lambda 2 as a parameters, but we also have all kn, all the vector of all the possible colors of your client. So basically, I used very simply the chain rule to calculate the probability, the conditional probability of many parameters. And here you have the likelihood, right? What does mean this? This means that for each distribution of colors, if colors is like old and young people, you have a kind of plot like this. It's like a pancake, right? So each plot is basically related to the color distribution. Now, since we can pose like many different questions. We can pose a question like, what's the ratio between old people and young people? This is one possible question we can ask, just given this model. Another one is, what's the characteristic decay time, like lambda 1 and lambda 2, right? This is the question we are interested in at the moment, right? To do this, we need to sum up all the cake, right? We need to sum all the flour because we calculate in this way the marginal distribution, right? Now, this is a little animation to show you how the marginal distribution is calculated. And in the X and Y axis, you have lambda 1 and lambda 2. Just I ask you to focus on the left side. The left side on the top is the starting point, and on the bottom, you have the solution. As you can see, you have a plot which is symmetric with respect to the diagonal. This is normal because we are talking about binary distribution, right? So you can call lambda 1, lambda 2, or lambda 2, lambda 1. You can exchange, doesn't matter. But as you can see clearly, we have in our data two different decay time. One is around 7, and the other one is around 2. And actually, this is the correct answer because I generate the data and I generated the data like this. So basically, your model is improving. And something that you can do, as I said before, with the denominator, so the multi-dimensional integral that you have in the denominator, you can directly compare and see which model is the best model. Now you have a broad overview and how you can use Bayesian statistics for this very simple model, but this very simple model can be generalized straightforward to very complex problem. I go back again to a very simple model because I'm going to go after to explain some application in finance, which is going to be very quick. I don't want to spend much time, but I tell you where I started from, right? I mean, just to say that Bayesian statistics is very simple. Imagine I flip a coin and I ask you, what's the probability to get head? So you will immediately reply 50%. But now what about if I flip this coin, right? This coin is a Mark Aurelius coin by the ancient Roman Empire, which is not really round coin, and maybe the matter distribution is not really homogeneous. So basically, you start to be uncertain. So your way of thinking is going to be like Bayesian thinking. You can say, based on my experience, the probability is 50%, but now I'm uncertain. Or in the video, I show you like a Bayesian machine is working for this example. So basically you're flipping the coin, the Bayesian machine is observing the phenomena and updates. I'll just show you if it works. Voila, so the Bayesian machine now is updating after 2 observations, after 10 observations, after 20 observations, and as you can see, quite quickly, the machine recognized that the probability to get head is 80%, right? Because it's the way I generate the data. Now, this example looks very simple, but it's very instructive because here you have, sorry, I just put it back. So at the end, oh, Jesus. Voila. So anyway, at the end, you see that basically your curve is getting narrow, narrow, and narrow, which means basically that the machine is learning and is less uncertain and less uncertain. Now, so far I've been talking only about the likelihood function. What about the prior? The prior can be very interesting function, but at the same time can be very dangerous. I show you with this other example why it can be very important and why it can be very dangerous. So imagine I flip the coin, right? But imagine you are an old guy investor who doesn't believe in digital transformation, then machine learning and Bayesian statistics. And he says, I'm going to calculate with my old pocket calculator, what's the probability of the coin. And then imagine you have another guy instead who's using, the investor B, who's using Bayesian statistics and also use an informative prior. But the informative prior comes from the fact that maybe his grandparents, when he was a kid, he was telling him that the probability to get head is more probable than getting tail. And instead, investor C is measuring instead the matter distribution, and he realized actually that the probability of getting head is pretty much very low. So in this case, you have 2 different priors. I show you how it behaves. This is a simulation. So as you can see at the beginning, the old guy has no clue. He has to observe instead. The investor C is always very close to the real answer, and the uncertainty is much lower. So the most important part is that all of them, they will reach the same results, right? Because all the approach, they are correct. The difference is that investor C is much faster because he's taking into account some information, which is a physical information, the distribution of matter in the coin. Now, very importantly, imagine to all of you, I give you 1 coin. Each of you, 1 different coin. You flip and the result of each of you will be different because the events are uncorrelated. But now imagine that I take all the coins and I put them together with a wire, like in a collar, right? Now, if you flip the coin, your result will influence the results of your colleague and all the others. Now we have a correlation of the results. So why I was posing this kind of problem, because flipping the coin and getting head or tail is a binomial distribution, right? So you can have either one or the other one. And if you have many of them and they are connected, they are intercorrelated, it sounds any bell with you? I mean, this is the stock market, right? So basically we have exactly the stock market behavior. So you can imagine that one single coin is one stock, And if you have other stocks and they are interconnected, you have to determine parameters. Okay, I basically was working as a consultant in Zurich for a financial company. Okay, this is the equivalent of the Bayesian behavior when the machine is learning. In that case, you had a distribution of the head and the tail of the coin. Here instead you have many parameters, right? Because now we have to determine like the average return and the covariance matrix of the stock market. And one, I was using this for a company in Zurich, fintech, and basically they are using Bayesian statistics for allocating assets. So basically what happens, you need to determine the average return, you need to determine the covariance matrix of among all the assets in your portfolio. And what you do is, like, as you can see into the right at the bottom, you do the inference of the average return and the volatility of a single stock. Here, for convenience, I'm showing you only one stock, but basically the universe, in that case, it was 14,000 stocks altogether. And you calculate expected return and volatility. As you can see, the machine, it was adapting by the behavior of the stock market. And as you can see, instead into the left, you can do some risk management, because a Bayesian statistics, as I told you before, allows you to predict and projecting actually the current statistics that the machine has been learned. And if your curve is inside your risk, this is called the one that you see in gray is called Bayesian cone. Now, if your performance of your portfolio is within Bayesian cone, the portfolio is behaving the way you were expecting, otherwise is outside. And to the right at the top, you have the allocation of your portfolio based on the Bayesian statistics. What the big advantage of the Bayesian statistics? Very well, the biggest advantage is that imagine you are the best friends of Elon Musk, and imagine that Elon Musk one day just casually, just to say, in an hypothetical world, is coming to you and telling you, you know what, I decide to buy a lot of Bitcoins tomorrow. So now you have an information which is a very important information for your portfolio, especially if you have Bitcoin in your portfolio. But even if you don't have Bitcoin and instead you have Tesla, Tesla is very correlated with all the assets that you have in your portfolio. Then manually you can put in your Bayesian statistics your prior knowledge, which comes from a very trustful sources with Elon Musk, and basically your portfolio can be rearranged accordingly, right? So with this, I hope I have been quite clear, and I hope I show you that Bayesian statistics is very simple, but it can be very complex if you, I mean, it's very straightforward. The complexity comes is a numerical complexity, right? So, but that's why you use a numerical solution, like you use after different technique for doing sampling, like Monte Carlo, like Markov chain Monte Carlo, or variational Bayesian statistics. Okay, with this, I hope I did my job. I want to thank you, everybody, for listening. Thank you.